Section 5.5, Trapezoidal Rule. So at the beginning of Chapter 5, or Unit 5, we focused a lot on rectangles and using them to find the area under the curve. In 5.5, we cycle back to that idea, but instead of using rectangles, we're going to use trapezoids. So the region between a curve and the x-axis can be approximated by trapezoids. The trapezoid should fit the curve better than the rectangles that we used in 5.5. So these areas will be a lot more accurate than the areas that we found in 5.1. So in order to do this, we need to remember that the area of a trapezoid is 1/2 h times b1 plus b2. So if f of x is non-negative over the interval from a to b, then the integral from a to b of f of x dx can be interpreted as the area under the curve. So if we look at this graph, right, each one of these is considered a trapezoid. Okay, trapezoid is a quadrilateral with two parallel sides, which each one of these has. So each one of these spaces here is called a subinterval, which we know from 5.1. Our subintervals are the h's in my area equation. Okay, so each subinterval is an h. The b1 and b2 are all the y values, right? These are so the base 1 and the base 2 of my trapezoid are considered my y values. So base 1 here would be whatever y is there. Base 2 here would be whatever y is there. Okay, and then for this trapezoid, you have base 1 here, base 2 here, so on and so forth. So generally, what we would need to do is we would need to add all the areas of those trapezoids to approximate the area under the curve. So we have 4 trapezoids, so we would need the area of all 4 of these trapezoids, and we would add them all up. So for trapezoid number 1, right, our equation for area is 1/2. Our subinterval here is h, and our first base is y1. Our first base is y0, and our second base is y1. For our second trapezoid, again, we have 1/2. Our subinterval is h. My first base is y1, my second is y2, so on and so forth. So because all of these have the same subinterval of h, we can factor out a 1/2 h from all of these terms. So if we factor out a 1/2 h, then we're just left with what's happening in the parentheses and adding them all up. So we have y0 plus y1, that's my first parentheses, plus y1 plus y2, plus y2 plus y3, plus y3 plus y4. Okay, now if we look closely, we can see that my y1s occur twice, y2s occur twice, and y3 occurs twice. y4 and y0 both occur only once because they're the first y value and the last y value. So we can rewrite this as 1/2 h times y0 plus 2y1 plus 2y2 plus 2y3 plus y4. Okay, so that is the trapezoidal rule. Okay, so the integral from a to b of f of x dx is approximately 1/2 h times 1y0 plus 2y1 plus 2y2 plus 2y3 plus 2y4, so on and so forth, until you get back to 1yn, which is your last y value. And this only works if the integral from a to b is partitioned into subintervals of equal length. If they are not of equal length, then you cannot use this rule. You would have to find the area of each individual trapezoid and add them together. Okay, so to make your subintervals of equal length, you would take the upper limit minus the lower limit and divide by the number of subintervals that you want. So for example, number 1, we want to use the trapezoidal rule with n equals 4. So this is how many subintervals we want. Okay, and we want to estimate the integral from 1 to 3 of x squared plus 1. Okay, so to find our h, right, we want to take my upper limit, which is 3, minus my lower limit, which is 1, over the number of subintervals I need, which is 4. So we have 2 over 4, which is 1/2, or 0.5. Okay. So to create this table, we know we're starting at 1, and our subintervals occur in 0.5 spaces. So 1, 1.5, 2, 2.5, and we're ending at 3. Okay, so now to find our y values, plugging into the equation that was given to us from the integral. So we want 1 squared plus 1, which is 2. 1.5 squared plus 1, which is 3.25. 2 squared plus 1, which is 5. 2.5 squared plus 1, which is 7.25. And 3 squared plus 1, which is 10. Okay, so since all of these have the same subinterval length, we can use the trapezoidal rule. So we have 1/2, and our subintervals went by 1/2, times our first y value, which is 2, plus 2 times our second y value, plus 2 times our third y value, 2 times our fourth y value, plus 1 times our last y value. Okay, so this is approximately 1/4 times 2 plus 6.5 plus 10 plus 14.5 plus 10. So approximately 1/4 times 43, which is approximately 10.75. That's the approximate area under that curve. So now let's look at some more problems and how trapezoidal rule can be used in that. So the velocity in miles per hour of a Piper Cub aircraft traveling due west is recorded every minute during the first 10 minutes after takeoff. Estimate the total distance traveled during the first 10 minutes using trapezoidal rule. So first thing we need to identify here is the fact that our units are not the same. So time is in minutes, and our velocity is in miles per hour. Okay, so our unit of time is different. So if we want our answer to be in velocity, right, if we want our answer to be using the same time units as velocity, then our time has to be in the same units. So each one of these intervals is not 1, it's 1/60, because 1 minute is 1/60th of an hour. Okay, so that's the first thing. So we want to estimate the total distance traveled during the first 10 minutes of using the trapezoidal rule. So we want to use the trapezoidal rule for each one of these intervals to estimate the total distance traveled. So the trapezoidal rule states we have 1/2 times whatever our subintervals are. So our subintervals here, even though we're going from 0 to 1, 1 to 2, 2 to 3, so on and so forth, those distances are actually 1/60th if we want to keep the units in hours. So our subintervals are actually 1/60, right? And our first y value is 0, plus all of these will be multiplied by 2. And this one at the end will only occur once. So we have 2 times 50 plus 2 times 60 plus 2 times 80, so on and so forth. Okay. So when we calculate all of this on the inside and these two pieces on the outside, we have approximately 1/120 times 1515, which is approximately 12.625 miles. Okay, so now for the next problem, we have a car travels on a straight track. During the time interval 0 to 60 seconds, the car's velocity measured in feet per second is a continuous function. The table shows the selected values for v. So again, we want to make sure that our units of time are the same. So t is in seconds, v of t is in feet per second. So we don't have to change any of the intervals here. We know that the time intervals are going to be the same. So we want to approximate the distance in feet the car travels from t equals 30 seconds to t equals 60 seconds using the trapezoidal approximation with 3 subintervals determined by the table. So this wants us to just look at t equals 30 to t equals 60. So all of this happening before does not matter. We just care about this last piece here. And we want 3 subintervals that are already determined by the table. So if we look at the table, 30 to 35 is one subinterval, 35 to 50 is another subinterval, and 50 to 60 is our third subinterval. So we have 3 subintervals, and they are not of the same length. So 30 to 35 is 5, 35 to 50 is 15, and 50 to 60 is 10. So we cannot use the trapezoidal rule. We have to find the area of each individual trapezoid. So to do that, we're going to use the area of a trapezoid equation, which is 1/2 h b1 plus b2. So we have 1/2, and for our first trapezoid, our subinterval is 5, so that's our h. Our b1 is our first y value, which is negative 14, plus our second y value, which is negative 10. Okay, and we're going to add to that our second trapezoid. So our second trapezoid has a subinterval of 15, so we have 1/2 times 15, and the first y value of that subinterval is negative 10, plus our second y value, which is 3. And then our last trapezoid has a subinterval of 10, and our first y value is 3, and our second is 10. So when we do all of this math out, this becomes 60 plus 97.5 plus 65. And if we add them all up, we get approximately 222.5 feet. So, one really important thing for this problem is remembering that when we use trapezoids to find the area under the curve, okay, f of x has to be non-negative. Okay, so that means that every value of v of t has to be non-negative. We're taking the absolute value of those. So negative 14, although I wrote negative 14, I really just took 14 and added 10. Okay, because I want the absolute value of these. So this equals 14. This is 10. And that's 3 and that's 10. Okay, so what we're doing is taking the absolute value of all those negative numbers so that our trapezoids have non-negative y values. Okay, because we want the area under the curve. The area is positive.